And we're going to use what we did last class to remind us what a logarithm is. And then later on, we're gonna do, actually, this should say part one, where I'm splitting up the log properties into two parts. So today we're doing part one. I don't have a warm-up for today. Let's see, maybe, do I have one later? No, I don't think so. We'll see. I'll do that. So we are going to start with logs, okay? So let's take a look. Let me make sure I'm recording. And we're going to end with all this stuff. So let's go on this little journey. Start with 5.3. Hold on. Did I write this right? Yeah, 5.3. Today is May 3rd. Oh, yeah. So logarithmic functions. And before we jump into the algebra, let's just kind of introduce, because I know logs are probably like out of trig, maybe the other most confusing function because of the notation of it. And so what we did last class is we did exponential functions. And we saw that they end up looking, the basic general form, they end up looking like this. And we kind of looked at their graphs. And we saw that for exponential functions, we're thinking of growth or decay, it seems to start off growing very slowly, and then it just increases really fast, right? We did the example with I start with 25 cents, then I double it, 50 cents, and $1. And then at some point, shoom, it just started growing really fast. And so anything in the real world that has initial slow growth, and then how did I say it here? Extremely fast growth afterwards. Usually there's some kind of exponential modeling or function that's being used there, right? So what we're going to see today is that logarithmic functions are going to be the inverses of these. Okay? So that means that the behavior that an exponential function has, a logarithmic is going to have the inverse behavior. So what do you think that would look like if it has an inverse behavior to an exponential?
It's going to grow fast in the beginning and slow later.
Exactly. So initially it'll increase or grow really fast, but then eventually it slows down. Okay. I wrote down here some examples. So like babies growing, when a baby's growing, when they're first born, like the amount of change that a baby has is like super extremely fast, right? Development, speech, but then down the line as you're growing up, maybe growth wise it starts to kind of level out, and then the change doesn't change as fast. Okay. Another one is like when you have I don't know if you've ever had like an anxiety attack. It's like very intense feeling, and then slowly, maybe through some breathing, you kind of start chilling it out a little bit. But that initial amount, that initial anxiety feeling you get in the beginning is very extreme, right? And so that's what log functions are going to help us model. So for log functions, we're going to see what those look like. Actually, let me write it down here so I can use this space. We're going to see what they look like, but yes, we're going to see that for log functions, they do the opposite. So it's initial extreme growth, the beginning, and then ends up being slow growth. Give me another example. Can you guys think of something else that starts off like really fast and then kind of levels out? Square root function? Okay. Yeah, that kind of changes really fast and then eventually kind of levels out a little bit. That's interesting. Yeah, that does have a similar behavior, but I guess it's not the same behavior since log is a different function. But yeah, you're right. It's pretty similar. One more. Any other example you guys can think of?
I'm thinking like starting a business, like it's a lot to start it, and then while you're in it, you just have to
Okay,
like fill up what you already have bought.
gotcha. So like all the stuff that, all the things that you need to do in the beginning are very extreme, but then it kind of chills out. Cool, okay. Yep. So let's use our knowledge of exponents to kind of see what this is gonna be like, okay? So what I want you guys to do is notice the difference between me writing 2 to the power of y equals 16 versus me writing 2 to the third power equals y. What do you guys notice about the unknown for these two here? The unknown being the y variable. Yeah, exactly. So usually we write an exponent to the things that we don't know, right? So I could also have written it like this. But we use variables to just say, what is that number that we're looking at? But yes, in terms of a question, this question is asking you to find the exponent. Well, this one gives you the exponent, and it just says, what happens when you raise the base to that exponent? Okay, so those are the very important key things to notice here. Here, the exponent is unknown, and here the exponent is known. So for this one, what is that exponent? 4. 4, right? 4 is 2 to the fourth power is going to give you 6. Yeah. But this 4 has a special name. It's going to be called the logarithm of this situation. Okay. But so here, this unknown here, the unknown for this particular example that I'm giving you, the unknown exponent is going to be 4, which the fancy name for all this is it's going to be the logarithm. Is there an I there? No. Logarithm base 2 of 16. That's how we're going to read that. Like that. It's not just 4, you're specifying that this 4 is being used as an exponent with the base 2, and it'll equal 16. And that's the mathy way of writing what that's saying.
Can you just say log base 2 or something?
You could say log base 2, but formally it'll say logarithm base 2. Yeah.
How is it not, because 2 of 16, if you looked at it by itself, would just be 32, how does?
Yeah. So here you're not thinking of 2 times 16. And so that's part of what I before I jump into the algebra, the confusing stuff for students is the vocabulary and the notation of it. Because then you do all this algebra, but you're not really sure what you're doing with it. Yeah.
You're saying is that kind of like right to left when looking at the equation?
Yeah, exactly. So you do it right to left, but this phrase right here tells you that 2 is the base, and this of 16 tells you it's going to equal 16. But the fact that this is what the log equals, log base 2 of 16, tells you 4 is the exponent. That's what's key. Is that every time you guys are finding the log of something, whatever it equals, it's going to be the exponent to an exponential problem. Okay. And so the way you understand this, I think it's probably easier to understand it this way. But the way it's converted into notation is we're going to write it log base 2 of 16 equals that number. But for it to equal that number, that's the special exponent that when I raise 2 to the power of that exponent gives me the 16. So that's where the vocabulary and the notation.
So if we put log 216 in the calculator, it's gonna say 4.
If you put log base 2 of 16 in the calculator, it'll be equal 4. But here's where we're gonna learn all this stuff. A calculator can't do this for you. There is no log base 2 button on the calculator. Okay, but we're gonna learn how to figure it out anyway with a calculator down the line, using some of this stuff from this ending section. Yeah, if you guys look in your calculator, there's a log button, and there's another kind of loggy button that says LN. But those are gonna be different. Those are different, yeah.
So, with the calculator, wouldn't you just use the subscript?
Some calculators are pretty fancy and there's a subscript, correct? But most don't have base 2. But you're right. Some calculators have a subscript. Here's another thing, when you're like, the format of how you write this, the 2, as you're saying about here, is a subscript, bless you. And this 16, this is not math, this is just the way you write, it's like format. Should be the same, same font size as the letters LOG. Okay, it's just because I see things like this. Like, so that means that can mean something completely different. So I just want you guys to get, like, start practicing the notation correctly. It's like a language class, right? Put the accent on the right spot, put the, whatever language and characters you're learning. But yes, this 16 should be the same font size as that. But when you guys see this is very confusing because it's notation you're not used to. But in reality, it also just means this. These two mean literally the same thing. They're just written different ways. This one's equaling the results of an exponential problem. This one's equals the exponent.
If the base was 3, would it be log 3, or was it is only 2?
No, that's exactly right. So, so these two things are equivalent, mathematically equivalent statements. They just look different. And so now going off of what you just said, Leah. So in general, if I have an equation written in exponential form, so if I have some base and I'm raising it to the power of some number x and it equals some other number y, then this is going to be equivalent. I can write that exponential form equation in the log version. Notice the base here is the same base as this little subscript. So here it's going to be log, what's the subscript that I use? Little b, parentheses inside of the log. The log has to equal the exponent. So it'll be, which one's the exponent? X, so it has to equal the exponent. So it's log of base b of 1. A little bit more about notation. So you don't have to write this part, okay? But like when you write something like this, does this mean 3 pi times sine? No, right? It's function notation. You're plugging in 3 pi inside of the log, inside of sine. So the same thing is true for what you plug in inside of a log. It's like trig. It's like you're plugging in something inside of this log expression. It's not times. Okay? Yeah, right.
Can't you get rid of a log by putting 4 to the 10? Or 10 to the, yeah.
We're gonna talk, yeah, we're gonna use exponent properties to start canceling things out down the line. Yeah, exactly. So we're gonna see what I can do, for example, to maybe cancel out this log expression, right? Yeah, we'll get there, we'll get there. So let's see. Just a little check in here. So if I had log base 5 of 125 without a the calculator won't be able to do this for you if it's not the smart one. This is asking you, what question is this asking you? What exponential question is this asking? You?
What exponent of 5, well, what exponent above 5 will give you 125?
Exactly. 5 raised to what power
Yes.
gives you 125? So, right? So I'm gonna convert this. In your head, that's what you guys were doing. You're converting this. I'm gonna put question mark here, equals 125. So part of your homework will be, I have an equation in log form to write it in exponential form, and then vice versa. Okay. Knowing this is confusing, but when you think about it in exponential form, it's a little bit more clear, right? So it's going to be, what did you guys say? It's going to be 3, correct? Yeah, good. On your calculator, though, like I said, you only have 2 log buttons. You have the log, LOG, and the LN button. But those are special kinds of logs. Okay. So let me talk about that real quick. So you have something called the common log, which means when you see common log notation, it automatically means the base B is going to be the number 10. So when you guys see log of X, and then you say, whoa, where did the subscript go? There's no subscript. It automatically is going to mean log base 10 of X. Okay. So in your calculator, you have the common log button, which means you have base 10 button. That one that you see in your calculator. That one's assumed to be base 10. Okay. So go on your calculator and just real quickly do log of 100 and then do log of 0.0001 and see what you get. And then try to convince yourself in exponential form why that makes sense. So go on your calculator and do those real quick. Yeah. Let me know if you need help with the calculator. On the iPhone, if you use an iPhone, it's backwards. You have to put the number 100 on the iPhone calculator and then click the log button. You guys got it back there? Did it work out with the calculator? Let me see. Just check. We gotta make sure you guys can do this for the whole. Yeah. And that one doesn't. Yeah. So Aldo, what'd you get for the first one? 2. Okay. And for the second one? -4. And let's see whether that makes sense if I rewrite this in exponential form. Okay, if you rewrite this in exponential form, remember, when you see no base here, it really means base 10, right? So this really means in exponential form, 10 to the power of 2 equals 100. And that's true, right? 10 times 10 equals 100. This one in exponential form means
To the power of -4 equals
0.001. And let's see why that one might make sense.
1/10.
We learned yesterday that really means 1/10 to the 4th. And 10 to the 4th is 1 with 4 zeros in front, so 10,000. So 1 divided by 10,000 will give you this decimal. Okay? Yes. So
Is there a reason why common law is based?
yeah, I think this is my reasoning why we as humans use a base 10 system, So a lot of the calculations we can deal with have to do with powers of 10. Exactly. Yeah, so we want to convert things in powers of 10. And so when math comes up, my guess is that a lot of the logs you have to use need base 10 because things we write are mostly in base 10.
So it's just more like a formality, more helpful reading.
Yeah.
It's European. The
Yeah.
metric system.
Mhm.
Sweet.
Why don't they put the 10 here? I have another reason why I think that happens. So back then, when you would write math papers, when there were computers, you had to, and let's say back then, when there was typewriters, typewriters wouldn't do like fancy math symbols, stuff like that. So usually, like if you guys go to like a antique store and you find a math textbook, like from back in the day, all the fancy math symbols are written with pen. So it's like you type all the writing you need, and then you go back and then you do all the math symbols by hand. I'm guessing people didn't want to like overdo that. And so it was understood, hey, I'm just gonna omit the 10 here, which means it's convention, we're gonna agree that that's gonna be base 10. That's like my own reasoning, like why I think that's true. Because I tried looking it up and I can't find any answers.
That makes sense to me.
Yeah.
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 I would do the same thing.
Yeah.
Just more anti-script.
Yeah, because if we look at the other one, so the other one's called the natural log. And then that one's gonna use base b equals that irrational number e. And again, why are we using that one? Well, like I mentioned on Monday, a lot of natural science and finances uses exponential functions. So a lot of, you're gonna see to solve things with exponential functions, you're gonna need to use logs with base e. Okay, and so similar reasoning that I just said is why I think this notation is used a lot. And so when you guys see ln of x, it really means log base e of x. All of them should look like this. They should all look like logs base something. It's just that this is like shorthand notation. But it's your duty as the student learning this to understand when I see log with no number, it means base 10. When I see ln, it means base e. Okay. So now on your calculator, do ln of e, and then do ln. See if you can do this one with a calculator. If you don't have the fancy ones. Let me know if you need help. It's all the text stuff.
How do you get E?
Each the power of one.
Let me know if you need help with the second one on your calculator. iPhone, and then press 1 over x, if that's reciprocal. Hit that button, and then you do ln. Calculator wise. Yeah, you will time.
Oh, negative. Okay. Yeah.
That's the only one who Okay, so what are you guys getting for the first one? You're getting one, let me move this down a little bit. You're getting, you guys said one? Okay, and let's see why that makes sense. Remember, ln really means log base e, right? So how would I write this in exponentially? E to the power of, actually, let me do this. Maybe you might see it this way. Look, this really means this.
Yeah.
Like that, right? So I'm gonna do E equals E, which exponentially, right? That makes sense? E to the power of 1 equals E. Now for this one, what did you guys get? -1, and that's because this is log base E. And so I'm doing E to the power of -1, 1 over E. Is that true? Yeah, right, because it's a reciprocal. Okay. Now, let me just have you do this as a extra one. So see how here we did the log of 100 equal 2? Would ln of 100 equal 2 as well? Before you click anything on your calculator. Let me have you guys think, should it equal, if this equals 2, if I put this in the calculator, will it also equal 2? If it did equal 2, how would you write that in exponential form?
E to the power of 2 equals 100.
E to the power of 2, does that equal 100?
No.
It does not equal 100. The reason this one equal 2 is because you have to understand, this is base 10. That's why it equal 2. Here, this is a completely different base, which is why it will not equal 2. What does it actually equal? What does it equal? 4 point some crazy 605 and then so on. So what does that number represent then? What does that number mean? That weird
E to the power of that.
E to the power of that weird irrational number somehow equals 10, 100. That's what that means, yeah. That's what that means. And so that's why when you guys are going to do logs, sometimes you're going to get these really weird irrational numbers. Because those are the weird irrational numbers that when raised, e raised to the, or the base raised to those weird irrational numbers are going to give you what's inside of the log. Okay.
How would we write that? We write that log.
This one?
Yeah. We write it log. E, just like that, just the one thing,
This guy right here. Or this one.
that one.
This one, no, what we're doing is we're writing it from log form and we're rewriting it in exponential form. So that's kind of what we did here. So this right here is equivalent to this, but in exponential form.
So that one you won't be able to write it in log form because it has it even,
This one is, when you write it like this is in log form,
but it's written like that because there's even.
but it's written with the letters ln instead of log because it's shorthand notation for log base e. It's telling you that the base is e.
So basically for that one, the log in that case, which
Is the ln, exactly, yeah. Yeah, good. So see, there's all this weird notation stuff, right? That I know when I was a student, I was like, I don't even know what the hell I'm writing. I just know how to do all these rules with it. But it's important that you know what you're writing. Okay. Well, let's see, so. Let's start thinking about it now as a function, but we'll lead our way there. So consider the exponential function. F of x equaling 2 to the x. It's a good old 2 to the x. this is what we did on Monday. Let's do a little XY table here. And we're gonna plug in some negatives and positives, okay? So we're gonna do -2, -1, 0, 1, and 2. Okay. So when we plug in -2 in for X, what does this become? 2 to the power of -2,
1 over 2 to the power of 2 is 2,
which is gonna be 1 over 2 to the positive 2, which is gonna be
4,
1/4, which as a decimal is
0.25.
0.25. And so we're gonna do that for the rest. So this is 2 to the power of -1, which is 1 over 2 to the positive 1, which is just 1/2. 0.5. 2 to the 0, anything to the power of 0 is gonna end up being 1. Any non-zero base, the power of 0 will be equal to 1. Okay, 2 to the first power is 2, and then 2 squared, 4. Okay, let's see, so. Yeah. So let's just do a couple points. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. All right, this is X and Y. And let's just plot those points as careful as we can. So at -2, the Y value is 1/4, so it's 0.25. So it's gonna be like right there. At -1, half, so we're halfway up. And then at 0, it's 1. At 1, it's 2. And at 2, it's 4. So this is matching what we did on Monday. Like that. Is that right? Is that a 1-to-1 function?
Yes.
Yep. Any horizontal line will cross it. How many times? Once only. So it's a 1-to-1 function. So therefore it has a
Horizontal.
An inverse.
it has an inverse function. So this is a 1-to-1 function, and so it has to have an inverse. So what we're gonna do is we're gonna find it. Okay. So let's find its inverse. F inverse. And let's see, let's remember, I'm forcing you guys to review here. What was your first step when you were trying to find an inverse of this one?
I changed the X and contributions. I just put this.
One step before that. Does this have a Y anywhere here?
Oh,
Change the F to Y. And then we're gonna do what B suggested, which is then you swap the X's and the Y's. And then our goal is to do what?
Isolate the Y.
Isolate the Y, and this is where it's like weird, because we can't do like the Y root. Right, so we do know how to write an exponential form equation into a log version of its equivalent log version stuff, right? So how would I write this in log version? Which one's the exponent? The Y, so this better equal the exponent, right? So it's gonna be Y equals of X. Have we isolated Y?
Yes.
Yeah, we isolated Y. Okay. So this becomes the inverse function. The log base 2 function. Okay, so from what we get here is that the inverse function of 2 to the X is gonna be the log function, log base 2 of x. And so, if I try to draw an XY table for this guy, I'm gonna be careful how I do it though. This is the inverse function, right? What do we know about the points of the inverse function and the points of the function? What's the relationship between them? They swap. The x and y coordinates swap. You guys remember that? When you get on the test, you got the x and y point and it should swap. So these are the points that you got from the function f. So then if I swap the y's and I put 0.25, if I put 0.5, if I put 1, 2, and 4. Let's just double check. Let's see. I'm gonna plug in, let's start with the 4. Plug in the 4 into the log function. So you're gonna get log base 2 of 4. 2 to what power equals 4? 2. So 4 comma 2, 2 comma 4. So it's mentioned. Here we're gonna plug in log base 2 of 2. 2 to what power equals 2? 1. Then I do this for the other ones. 2 to what power equals 1? We did that here, right? 2 to the power of 0, so that better equals 0. And then we just fill it in for the rest. We saw that 2 to the power of -1 equals a half. So this is going to be -1. And we saw 2 to the power of -2 equals 0.5. So this has to equal to -2. Okay. But now we're looking at this as a function. Okay. Let's plot those points. Let me start over here. So we got 4, comma 2. 1, 2, 3, 4, comma 2. Then I got 2, comma 1, 2, comma 1. 1, comma 0. A half. And then -1. And then a 4th and -2. And so notice that when you connect these points, everything you learned about inverse functions is matched. Meaning, remember, if this is the graph of f, and this is the graph of f inverse, you guys remember the symmetry across the diagonal line? There was symmetry across the diagonal line, and if not, it's okay. You still got some to review, right? But yes, so let's go back to the very beginning of what I said. Exponential functions, they're initially increasing slowly, and then they increase really fast. Exponential functions are increasing really fast, and then they're going to end up leveling out and changing slower as you go. Okay. Okay, so that's mentioned. Questions on this part here? Yeah.
So the inverse would have a vertical asymptote at y.
Yeah, good observation. Yes. So notice that the exponential function had a horizontal asymptote at y equals 0. The log function, yes, is going to have, let me choose a different color. I'll just do, let me erase this one. Yes. It's going to have a vertical asymptote. We have a vertical asymptote at what?
X equals 0.
At x equals 0. Okay. Cool. Hold on. What do you notice about the domain of this function? of the log base 2 function. Let's just add as much detail here. So what do you guys notice about its domain? Can it ever equal 0? Let's see. Let's see, can this guy ever equal 0? If I did log base 2 of a number and it equals 0, or no, I'm plugging in 0, right? I'm plugging in 0. That means 2 to the power of whatever this is supposed to be equals 0. But does this function ever equal 0? Does it ever reach the x-axis?
Oh, no.
It doesn't, right? No number, no matter what x value you plug in here, this will never equal 0.
Yeah.
So this will never equal 0. So what that means is that for the log base 2 function, you can't plug in 0. Okay? Even if this was base 10, or even if it was base E. Try doing that real quick. Do log base 0 on your calculator or ln 0 on your calculator. Just so you guys can see. It says domain error, using the word domain, right? And that's because 10 to the power of a number can't ever be 0. And e to the power of a number can never be 0.
What's the difference between a domain error and a syntax error?
Domain error, in my opinion, is more like mathematically correct.
Okay.
Syntax is more like, I can't read this because it's not a it's not mathematically defined. Yeah, so notice the graph of this. 0 is not included. Are any negatives included
Yes.
on the graph of what the log function? No, right? So you're starting from 0, not including it, going to infinity. But what about the range? All of them,
So you can write a domain array for both these.
correct?
And
Correct.
so they would be fine.
Yeah. Yeah, and actually, you know what? Let me be more specific for your notes. This is gonna be the domain of F inverse. And then the range of F inverse. And as Kimmer mentioned, for F, it's swapped. The domain of F is the range of F inverse. And is that true? The domain of 2 to the x? It's all real numbers, right? The range of F is equal to the domain of F inverse. Notice, is the range of F 0 to infinity?
Yeah.
Correct. So everything that you've learned about inverse functions, it's like really ingrained in both of them.
Okay, can you just repeat one more time where we can't plug in 0 for the numbers? Because it has an approach 0, but like, what's it?
Yeah, so here, I'll write over here. And this is true for any exponential function, okay? So I guess let's put red remarks. Oh man, this red marker sucks. So the log base b of 0 is undefined for any base because b to the power of 0. No. Let me write it like this. Sorry. Is undefined because if it equals something, let's just say it equals a number n. If this equals some number, then when you write this in exponential form, what would that look like in exponential form? B to the power of n is equal to 0. But this will never be 0. You would use the knowledge you used on Monday. Exponential functions are never like this will never be 0. Some base to a number will never be 0. They're always above the x-axis. Okay, and so this can never be zero. So then this can't equal a number. Okay. And then the same is true if you try plugging in a negative. If you plug in a negative number. So you put in your calculator the log of -5, it's gonna say domain error or syntax error. Okay. Is also undefined. Because base to the power of a number is never negative. Right, these exponential function graphs are gonna be above the x-axis, so they're never gonna be. Well, that's gonna be important in the living. So let me just pull this down real quick. Okay. There we go. So let me just show you guys. Oops, I'm like. If I do y to the bx. Oh, just kidding. There we go, y to the bx. And if I do log base b, whoops, y equals log base b of x. Hopefully it shows me the graphs, isn't that show? Oh, b can be 1. There we go. From 0 on, it just can't be 1. So look, here's b being a smaller value of b. Whoa, chill. Okay, 1.5. Notice these graphs, the log graph, you can't plug in, it's never going to be 0. X will never be 0, see? So it's going to be a little away from the y-axis. And it's never negative because of the whole domain and range restriction of exponential functions. Okay, so this is going to be true for every base, even when the base is less than 1. Let's see. Let me double check that that's true. It changes a little bit, yeah. Okay, but again, the graph of the log function, you can't plug in 0 still, right? It has a vertical asymptote at x equals 0, and it's not on the negative side. Okay, I just wanted to show you that. Okay. See what time. All right, so we're going to put all this together that we just said. And so we're going to generalize it. So in general, for b not equaling 1, and again, being positive, if f is the exponential function b to the x, then the inverse function of it is going to be log base b of x, just the way we did it this way with the 2. Because it's also true if b is less than 1, like being a half number, like a half or a third. Yeah, I know, so specific. So what the homework's going to do is they're going to give you some of the graphs of log functions. And then they're going to ask you for their domain. But you have to use this knowledge, and I'm going to show you how you're going to use this knowledge. Right? Yes, these are inverse functions, but they have restrictions. Let's write that below. So here the domain of f equals the range of f inverse, and the range of f equals the domain of f inverse. And so what we learned on Monday is that the domain of f was negative infinity to infinity. And the range was from 0 to infinity. So you're going to use this knowledge here for more complicated log functions. And that's where it's going to start getting algebraic, man, you guys. It's going to give you an example of a more complicated log function, and it's going to say find the domain of f of x being the function, let's say log of 2x plus 1. They throw some more complicated expression in here instead of just an x. So what you're going to do is you're going to use these two things. It's kind of like, you don't have to write this down, but it's kind of like if I gave you guys and I asked you, what's the domain of this? What is it that you do in your head to start that point? If I asked you the domain. No, not quite. You don't want the fractions have their own restrictions, right? You don't want the denominator to be 0. So then you say, okay, when does this equal 0? And then remove those from your domain, right? Or if you had something like this, square roots have their own restrictions. What can you put inside a square root? Can't put a negative. So what is it that you did to find the domain? It can't be negative. It has to be either 0 or positive. But how did you write that mathematically? You used an inequality. You wrote when is x plus 2 greater than or equal to 0, and then you solve for it. Remember that from a few tests ago? But that's because they each come there with the restrictions, right? Each function had the restrictions. Well, in this case, this function also has these two restrictions. You don't want the inside of a log to be 0, and you don't want the inside of a log to be negative. So therefore, 2x plus 1 has to be what? It has to be positive. As an inequality, though, it's going to be greater than 0. Just the way you did it kind of for this one. Okay? So you don't want, this cannot be 0 or negative. So what you have to do on your own is you have to figure out when does 2x plus 1, when is that going to be greater than 0, and then solve for your x. So for the final, when you guys are making your cheat sheet, it would be good to remind yourself of the restrictions of rational functions, square roots, and now logs. Okay. All right, so then what do we do here? Minus the 1 to both sides. And then divide that 2. And then you get x equals negative a half. And this tells you that for this function, you have to plug in its values greater than negative. How do we write that in interval notation? Well, look at a number line real quick. Does it include the 1/2? No. Does it say it has to be to the right of it or to the left? The right of it, right? Not including. Yeah. This would be your domain. And that just means you have to plug in values from here to make this. Otherwise, your calculators means a syntax error or domain. And then the range would, yeah, be negative infinity to infinity. Questions? All right, I'm gonna let you guys decide. A more complicated example or a break?
Example.
And then a break?
Yeah.
Okay, all right. I like it, I like it. A little bit torture before the enjoyment. We already got this far, right? Okay,
Is that the end of 5.0?
no. Kind of, no. Lecture wise, yeah. Yeah. Okay, let's see, a more complicated example. Same thing, let's find the domain of, and this one's gonna say f of x is ln of x squared minus 4x plus 3. Okay. It's a log function. So the inside cannot be perfect, can't be negative or 0. So then therefore we want this to be, we need x squared minus 4x plus 3 to be greater than 0. But now I have a quadratic.
4 and 1,
Say it again?
4 and 1.
Well, let's see.
Which
Hold
one
on.
is we make?
We're, oh, hold on. There's a little step, a little algebraic step before that. You're trying to see what x values are going to make it positive, right? So to help you, you're going to want to factor similar to when you solve. So what does this factor into? It needs to multiply to positive 3. Negative 3, and then it'll be negative 3x minus an x gives you 1. Okay. So here's where it's going to get weird. Okay. So if this was an equation, what did you do if it was an equation from here? Set them each equal to 0. That you can't do it, and let me show you why that's not going to work. Okay. If I try to do this incorrectly, so this is the incorrect thing to do. And I set x minus 1 greater than 0, or x minus 3 greater than 0, and then solve for x, and you get x is greater than 1, or x is greater than 3. Let's put that on a number line to kind of see what this is saying. So x is going to be greater than 1, so left or right? Right? And let me go like this actually. And then x is going to be greater than 3. So what's an interval that describes that? 1, 2.
One to. Yeah, 1 to 3. And then.
Yeah, well, let's see, if we plugged in 3, if you plugged in 3, what would this become? 3 minus 1 is 2. 3 minus 3? 0. 0 times anything? So can this be 0? No, right? Logs can't be 0. So I need to exclude the 3.
Yeah.
Like that. Okay. But that's not gonna work. Okay. That's not gonna work. Is 0 less than 1? Can I plug in 0 here? Yeah, because it gives me 3, which is positive, right? Crap, that's not in this answer. So that's incorrect. You see that? Uh-oh. So what you're gonna do, there's several ways to do this, okay? But because I want you guys to review graphing, you can graph this quadratic function. And you can graph it. So let's graph. What we're gonna do is we're gonna graph y equals x squared minus 4x plus 3. And let's do a little review. What's the shape of this graph? the quadratic. So parabola, does it face up though, or does it face down? How do you know it faces up?
Positive.
What's positive?
The leading.
The leading coefficient. Yeah, good, good. So because this is a positive one, this says it's a parabola opening up. Because that's positive, right? So let's see. So if I was to graph this parabola, it's going to be positive. Where are the x-intercepts? If you know that it factors like this. 1 and 3. So 1, 2, 3. So it has to cross here and it has to cross here, but it opens up. So can you guys see the picture of what the graph might look like? It has to cross through here and here, but it opens up. So it's going to have to be like a smiley face going through those points. Is that okay?
But does it then give you a negative?
It does give you a negative. So you use this parabola and then you say, okay, when I look at the parabola, when will the y values be greater than 0? For which x values are the y values above the x-axis? But you got to write it in intervals.
So.
So when, let me write it like this, what I just said, for which x values will y be positive? Because that is what this is going to give you, right? So when will it be positive? As long as it's less than 1, right? So negative infinity to 1. Do I include values between 1 and 3? No, that's going to give you a negative y value, which means this will be negative, which means this will be negative, which is what we don't. Okay, so yeah, you don't want to include that, but then you do want to include this part because here the y values are positive, so that's 3 to infinity. And so that's why 0 was okay, because that was in this interval. That's why 0 worked. Cool. Okay. And so I think the homework, the highest ones are just quadratics. And it won't give you like third powers or fourth powers. I don't think so. But you could do it the same way. Just look at the graph of it. Okay. I think we've earned the break. Okay. So this one was easier to solve. When it's quadratic, you can't just do that. The algebra, okay, it won't work. So you're gonna have to look at the graph of what's inside to help you out. That's one way to do this. All right, let's take a break. Come back at 2:03. Oh, damn it. Let me show that. The video you watch it. I left the screen share. Yeah. All right, so if you guys can put the worksheet away. Or you can do it, that's fine. We're gonna move on, guys. We're gonna move on. Moving on. I'll post the solutions to that worksheet. After class. Okay, we're gonna jump more into the algebraic stuff of logs. The properties of logs. Part 1. Part 1. All right. So we're gonna do a little warm up, but I'm not gonna collect it. So let's compute the following. Help me out here. And then we're gonna compare them. So let's do 1, 2, 3, 4, 5, 6, 7, 8. Have you write that? Okay, for number 1, let me just write it down, then we'll do it. It's gonna be log base 2 of 8. Then log base 2 of 1/2. log base 5 of 25, log base 7 of square root of 7. And then on the second column, it's gonna be ln of 8 divided by ln of 2. And then ln of 1/2 divided by ln of 2. Ln of 25 divided by ln of 5. And then ln of root 7 divided by ln of 6. Copy that down real quick.
Check out what these right.
All right, we're gonna do the first column together without a calculator. Okay, so we kind of can't with the calculator, unless you get a pencil. So, let's see. You just practiced converting exponents to log, right? So this, we need to figure out a number so that 2 to the power of that number gives you 8. What is that number? 3. 2 to the power of 3 is 8. So this is gonna equal 3. 2 to what power equals 1/2? -1 because of that reciprocal property. Now we have base 5. 5 to the power of what is 25? 2. And then this one's a little trickier. 7 to the power of 0.5 or 1/2 can be represented as square root of 7, right? Okay, now what I want you to do with the calculator is I want you guys to compute these quantities here, since you have an ln button. So use your calculator and see if you can practice knowing how to type that in your calculator. It could be tricky, especially with the iPhone. Yeah. It's very hard with the iPhone.
Is that log 2 of root 7 or log?
This is log 7 of root 7, sorry. So you guys can do this in your calculator, I'll help you out. Let's see. It's not- How are you doing? I think what you're gonna do is you're gonna do 8 ln. Divide, and then do 2 ln. Enter. And enter. No. You got it in the calculator. Okay. Then cross-reference with your classmates, see if you guys agree, because I'm seeing all kinds of different answers. Yep.
I need to say. See it fine? This is so much
Like ones you got is certain. No, we're talking about the eyes, but we're already down. That's only good for.
Oh, yeah.
learns 2 plus 2 equals 6. Like, if you really think about it.
Like 2.
We've been doing it wrong this whole time. Because our brains. People are high.
But the size of this thing just came up with about.
Linear algebra.
Do you come to go back?
I think that's humans.
And then
Oh, yeah, they said who else like. this-
I didn't think that'd be like,
That's how we get some.
I was gonna take some serious,
Let's see. Same as the what? Same as the left. Good. All right, so what did you guys get here? 3. What'd you get here? -1. And then 2. And then 1/2. All right, any patterns that you guys noted here?
They're inverted.
No.
The
There-
denominator or the like log base, that's the other one.
The denominators are like the bases of this.
Yeah.
And the numerators are what's inside the logs here, right? So here's another magical thing I want you to do. Do the same thing, but do it with log instead of ln. Pretty magical.
Like log of it.
Do log instead of ln, yeah. Do what you get. The same thing, right? The reason I'm saying it's magical, because if we like really like take a look at it. This is supposed to be some number that you raise e to get 8.
Yeah.
Whatever the number that is. And then this is another number that e raised to that other number gives you 2. And somehow when you divide those two numbers, it gives you 3. Like when you divide two irrational numbers, you're giving you 3. I think that's pretty cool. And then not only that, for log base 10, right? If I do log base 10. Oh, sorry. Put that in your calculator. What is that? 2
It's 0.9.
and some other stuff, right? 0.9 and some other stuff. 0.9 and some other stuff. Okay. Now do log of 2.
Not 0.09, 0.9.
0.9. Give me a couple more just for fun.
Oh, 0308.
Okay.
Yeah.
Now, what about this one?
0.301.
0.3. Okay. And when you divide these two weird numbers, it gives you 3. See, that's pretty
Oh,
magical.
but
Right?
if you look at them, then that makes sense.
They're like tripling, right?
Oh,
And then, but now do ln of 8. Just by itself. What is that? 2 point some weird stuff, right? And then do ln of 2.
0.6931.
And see, you divided these two weird ass numbers and they give you 3.
Yeah.
I don't know, I think that's kind of magical.
Yeah.
Right? That's why I said, that, because it's like you're dividing these two irrational numbers, but they're equaling these perfectly beautiful integers. Okay? And not only that, but it seems to work for base E and base 10. Okay, and so that's not an accident. And so because calculators only have ln buttons and base common log buttons, there's a nice property that we'll be able to use on next week to figure out how we get that property, where I can rewrite a log of a different base into an expression of either natural logs or common logs, so that then I can use a calculator. Okay. Oh, sorry, hold on, I wrote a typo here. Oh, whoops. So. Since calculators only use common log and natural log. We can use the following. What's called change of base formula to compute any log expression. Change of base formula. How it's derived, we're gonna learn some fancy properties next week to see how we can derive it. But I wanted to show you to first because it can be very frustrating not knowing how to compute this on a calculator. Okay. Okay, and so this is what it says. It says for any positive real numbers, for any positive real number m, real numbers m, b, and n, it's a lot of them. Where n is not equal to 1, and b is also not equal to 1. All these conditions. We're going to learn how any log base b of some number m, kind of like we did here, can be rewritten as a log of a completely different base, n, but they just have to be the same log, same different base. Just the way these were both base e or base 10. And then whatever the base is of my original log, that's what I'm going to take to be in the denominator. The way we were seeing it here. All the denominators were the bases of the original log. And on the top, it's the same m that I was trying to take the log. And so not only will this work for base e or base 10, it's true for every other one.
Those are the ones that we want.
But those are the ones that you use in the calculator. So that's why this is going to be handy. Yeah, but
What is, I don't understand n.
n is a completely different base. So it's like this example. I can write this as log base ln, right? What base is ln? E. So this is log base e over log base e. But the original base is what goes in the denominator. It's when I'm taking the bottom log. And on the top, it's the original number I was taking the log. This is true for base e, but it's powerful. It's saying it's true for any base, as long as it's not one.
So how would you do that with just like any problem? Do we have an example for this? I'm confused.
Yeah, so it's saying that this basically can be written in infinitely many ways. I could, instead of e, I can have a random 3 here.
So if we were to so that's why we can use the calculator, because we can put in log and it'll work that way.
Because it'll work for either for n equaling e, which in this case is the ln button, or it can work if my base n is a 10, and so then I can use a common one. Yeah. Okay. Okay. Yeah, so I'm gonna kind of like summarize what I just told Bobby. So this change of base formula says that this log can be rewritten into a completely different log with a different base. So, if n is 10, then that means that every log can be rewritten as log base 10, right? Because n here would be tenths. So that would just be the common log of m over the common log of b. So then I can use a calculator to compute that. But if the base is e, now if my base is e, how are we rewriting this? Base e is just ln, so I can also just rewrite ln of my original n, but I divide it by the ln of my base, of my original base. So it's a way so that we can use a calculator to compute logs of different bases. That's kind of the tool that I wanted to show you here. You're going to need this tool because down the line, we're going to solve equations again. And the answers are not going to be nice. They're going to look really weird. And they're going to have ln's dividing ln. Okay? So we're going to need to know the decimal value of it. So you're going to need to know how to write any log using a calculator. So with your calculator and using this change of base formula, you can use either the common log or the ln. As you saw, you get the same answer as you just did right now. And that's because this is true regardless of the log. So on your, or with your calculator, compute, figure out what these are with your calculator. Do the log base 3 of 9, log base 3 of 7, log base 6 of 10, and then the log base 6 of 1 over 36. So see if you guys can use this change of base formula with your either the common or the natural log to compute these guys. And actually do it with, find the decimal value of it. You guys can figure out how to do the calculator. Do that real quick. Let's see. Yeah. And that's kind of the reason you. If these numbers are not a power of the space, then we don't know how to figure them out. So now with this tool, we can use a calculator. to figure them.
I just wanted to understand why. But well, here is actually well standard. It's not one of the. Oh, so that's why. Getting set below the same. I think it's going to be 6 love and something. Because we know it's not going to work.
All right, guys, so let's see, help me out. What'd you guys get for the first one? 2, which makes sense, right? 2 to the power of 3 is 9. So this, you didn't need a calculator, but it's just to show you to verify it, right? Did you guys do ln or log? Log, could you have done ln? You would get the same answer, right? You could have done ln of 9 over the ln of 3 to give you the same thing. All right, here though, this was not a whole number, right? 1.7712. Okay. So that means 3 raised to that weird number. It's gonna give you 7. What did you guys get for this one? 1.285 and some other stuff. And here, oh, that one was just a -2. Okay. And so you're gonna want to use some of this stuff in your homework, and we're gonna use it down the line. Okay, yeah, question.
Is there a rule that if it's like? This, like if you square the small, like. The smaller number, then it would be half because it's that, like, you know what I mean? Like since 3 squared is 9, it's 2, and since 6, like, to the -2nd. Or 6. It looks like it just doubled, I don't know, it looks weird.
Are you saying like if you looked at log base 6 of 9?
Yeah, would that be similar?
No, it'd be like a 6.
What is- I think you're asking if you double the base, what happens to the values?
Yeah.
Can someone help me? What is ln of, what would this be? One 1.226. Doesn't look like it's half or anything. No, I think it's a little different. Looks more complicated. We're gonna learn a lot more rules next week that can actually answer that question a little bit. Okay. All right, I'm gonna end, but I'm gonna leave you guys with a bonus, which is what Bobby just asked. Okay. So I don't know the answer to this. So if log base b of m equals a, can we use that to figure out what log base of 2b would equal of that same number? Which is general, I'm kind of like a mathy way to ask you a question. Oh, sorry, this b should be the same. So if you know log base b of m equals a, can you use this knowledge to figure out what log of 2b would be for that same 2a? And so we just did an example. It wasn't 2a. We just did an example. Yeah, we did log base 6, base 6 of 9, and it was like 1.2 something like that. So it was definitely not double of that. It doesn't seem to be half of it either. Okay.
That's the ones you've been trying to find all your life.
No, not quite, but now I'm interested, I wanna know, but I'll let you guys pick at it as well. All right, guys, we'll stop there. We'll end a little early. Someone's alarm just went off, they're ready to go. All right, guys, we're done, good job.
Up here for